Now let's look at some basic idea why we need finite element analysis. Now this is basically an in-depth explanation of the first slide. Now if you look at your first year physics or your high school physics, what we typically the problem that we typically do in first year physics are what we call rigid body problem. Rigid body problem. Now let me give you an example. If, say, I have a metal bar that look like this, and I fix the metal bar in one place. Now you know that the metal bar has certain weight, say G, I put a smaller font. Say this weight is 100 Newton. And you know that I can't possibly put this bar in stationary position if I just lay a hand on one side. So I need to give a force to it. Say I put 50 Newton of force, right? And then the question typically they will ask you is, what's this little force here that I need to put the whole thing into the balance? Now, when you look at this problem in first year physics, you'll say, okay, the whole bar is rigid, so it's not going to deform the shape. That means all the force being applied is actually used to balance the whole bar rather than deform it. Now, in that case, I can write the little f plus the big F equal to G, right? All the forces that are going up is going to balance the force that goes down. So in that case, I know this big F is 50 Newton and this weight is 100 Newton. So the force at this pivotal point that hold the bar together is going to be 50 Newton, right? Now this is all fine, but in a real engineering design, you can't possibly, or you can't simply think about this bar being rigid, right? Everything is going to deform either elastically or plastically. Now, it would be good if it deform elastically. That means when you remove the loading, the object go back to its original shape. But if you start to deform plastically, that means if you remove the forces, the things will deform. For example, if the car go past a bridge, it start to plastic deform, the bridge will change its shape and it might not be stable anymore. So if we go back to this metal bar problem, right, we still have this metal bar that look like this. Now say if I fix the bar at this point and start to apply a force at this point. So if say this weight G is still 100 Newton and apply a slightly bigger forces to deform the bar. So this bar will start move, right? But it doesn't move like this pen just turn in this way. It might start to bend a little bit, even though you might not be able to see it perfectly. You might do something like that. Of course, this is an exaggeration. So this bar will start to deform. And as you can see, the deformation at different part of this bar is not going to be the same. Right, you have a larger deformation at the end and smaller deformation in the middle, right? So the forces on this bar, in this case, you can't think of is just being applied to the end of the bar. Actually, every part of this bar will experience some sort of forces that try to pull it up. And there will also be forces in the middle of the bar because everything is connected together. They try to do something to change its shape in this green color, right? So when you face this kind of problem, what engineering try to understand is if I apply a force at one end of the bar, what will be the deformation along this whole bar, right? Now, apparently, this kind of method, you can't just go back to this simple arithmetic to figure out what's going to happen. Because, first of all, you see this is a continuous object with some shape. And typically it might have an uneven distribution in its density. Uneven distribution in density. That means this whole bar might not be a uniform object, right? And the shape itself, okay, here I just show a sort of like uniform metal bar, but in reality, the shape, it could also be arbitrary, right? So in this case, we cannot possibly get an analytical solution. What solution? So typically is if I have a force, what will be the actual deformation, right? Deformation. Now, where does this come about? You can think about this in terms of the Hooke's law, where you learn in first year of physics, where if I have a force applied to a spring, the spring will start to deform, and the deformation, if it's under an elastic limit, is kx, where k is the spring constant, right? And if you plot this graph, it typically looks like this, where you have x, f, and is directly proportional to each other. Now, in finite element analysis, what we try to do is solve this kind of Hooke's law problem in a continuous body. So, for example, if I have a metal bar, I will actually divide it into different parts. And if I apply a load here, the whole thing is going to deform. But I can treat individual part of this bar as a little spring. Right? I know the whole bar is going to deform non-linearly with complicated shape. So the Hooke's law doesn't hold. But if I divide it into smaller elements, right, I can actually apply the Hooke's law in individual part and solve the deformation in the whole body. And in this way, I can understand how complex mechanical structure behave in real life. And the finite element analysis is an exercise basically establish a complex relationship between your loading and the force and the deformation in a real material, such that I can understand, okay, if, say, a car goes past the bridge, is the bridge going to permanently deform or just slightly deform within some tolerance? So this is a very important design question to ask in real engineering. Now, what we typically have is this value of k, right? You know, K in first year physics is called spring constant. Now, in the actual material design is describing the mechanical property of materials. For example, the Young's modulus, right? That's going to tell you how much material deform under a certain load. So with the knowledge of, say, the Young's modulus and a practical way to break down this continuous body into discrete finite part, we can solve for the deformation under loading again. So this is the basic idea behind finite element analysis.